Here we go, day 43. The goal is to interpret graphs to describe a relationship in the 3-minute review. The lesson is 5.2, rate of change. Word of warning, I am going to steal some of your class time tomorrow to do activity. There's going to be an activity, about a 20-minute, 30-minute activity, so you will have some time stolen away from you, but it will be practice doing this skill anyway, so it'll be all good. The graph shows Grandpa Ferd's annual salary as he grew from a teen until he retired in 1995. Describe the trend in Grandpa Ferd's yearly earnings graph. Be precise. So this is what we did yesterday, right? We can say that the graph, in very, very unprecise terms, we could say it increased slowly, then quickly, then slowly, but let's be more precise. We could say from 60 to 65, salary increased slowly. Then from 65 to 80, it increased more quickly. Salary increased quickly. And then from 80 to he retired, his salary didn't increase very much at all. 1980 to 1995, his salary increased very slowly. And today we're actually going to put numbers on this quickly and slowly business. That is the goal. Rate of change. Calculate and interpret rate of change in real life setting. The rate of change of a graph refers to how fast the graph is increasing or decreasing. We use a familiar formula or formulas to calculate a number for rate of change. So we talked that slow and fast and all that business, but how fast is it actually changing? Well, we use average rate of change is rise over run. Well, that's just the slope, isn't it? Well, we talked about rate of change way back in grade 9 as rise over run. We didn't call it average rate of change, but that's what it was. The slope was the average rate of change. Or we sometimes called we went change in y over the change in x, right? Where we, drew a triangle on the graph and went rise and run, change in y, change in x. And sometimes if we were given a table or maybe even points, we use this little formula, y2 minus y1 over x2 minus x1, and we've seen this already this year. That's the average rate of change formula. So let's see it in action. Calculate the average rate of change for each time interval. Now this is going to be a whole bunch of calculations, so let's sort of gear up. That's kind of like the x variable, and this is the y variable. Independent was year, it went along the bottom. Earnings is dependent, went along the side. And so here, these values are the change in y. These values are the change in x. And I can see the change in x is always up 5, isn't it? Up 5, up 5, up 5. And that's true for every single one. So I'm just going to go dot, dot, dot there. Here, the change in y, I can see, well, how much is it going up? That's not as easy to see. And if I can't remember how to calculate rise and can't see how much that goes up by, it's y2 minus y1 in a table. I can just do that, and that's 7,500 minus 6,000 is 1,500. So then the average rate of change for this one, average rate of change is change in y over change in x, or rise over run, 1,500 over 5, and that is about 300. Now, what does it mean in this case? That means over those years, his salary went up by 300 bucks a year. So 300 bucks a year. And that's what the average rate of change, the slope, means. Here, and I'm just going to go ahead and do these. You can maybe pause the video and do them yourself too, rather than watch me. I'll do maybe one more together. So y2 minus y1, the AROC is 7,000 over 5 years. Again, the change in x was 5 years, and that is about 1,400 bucks per year. Okay, I'm going to pause the video and do the rest of mine. You should do the same. Okay, hopefully you managed to fill those out, or you can pause the videos and get my my version as well. The next thing that we're discussing is how does this fit in with the graph from the 3-minute review. Remember, in the 3-minute review, we said it went slowly, quickly, slowly. We'll have a look. Slowly, right, small number of increase, and then more quickly, almost 2,000 bucks in the middle, and then slowly at the end, $200 a year near the end. So that matched perfectly, and in fact, it's a little bit better because we've got numbers to back us up as well. Great. Another couple of rate of change if we're given a table. Well, we just did one like this, really. So this shouldn't be too tough. On a table, I could go, you know, rise and run, or change in y and change in x. Certainly could. Well, from 14 to 13, I went down 3. From 1,000 to 8,000, I went up 8,000. Well, what's the AROC, the average rate of change then, is change in y over change in x is minus 3 divided by, not 8,000, 800. 800, which is about, well, 0.0037. Well, what are the units here? I mean, over here, it was dollars over years, right? Dollars increased over years gone by. This one's kind of weird. This is degrees Celsius and 800 feet. So what's the rate of change? This is in degrees Celsius per foot, right? Per foot, 1 foot. So that means for every foot we go up, the temperature drops by that amount, you know, a fraction of a degree Celsius. So for every foot of elevation, temperature decreases because it was a minus, dandy. This one is another graph. Time is the independent, and speed is the dependent. And I'm going to use a different formula. I'm going to use the good old AROC is equal to y2 minus y1 over x2 minus x1. So, well, what are these things? We certainly could put the points into a table, and if you like the table, you could do that. But the way I think of it, this is x1, y1, x coordinate 1, y coordinate 1, x2 and y2, and then I can just fill it out that way. 4.5 on the top minus 0.5 on the bottom over x2, which is 3, subtract x1, which is 1. Calculate this. This is 4 over 2, which is 2. What are the units? So we were talking about these graphs tell a little bit of a story. Well, the y coordinates was meters per second. That's the speed. And on the bottom, it's the number of seconds. So this is meters per second per second. Meters per second per second. Well, what are we talking about? We're talking about the speed change. The speed is going up by 2 meters per second per second. That's acceleration, right? That's acceleration. The ball's speed increases because it's positive by 2 meters per second every second. And for the folks that have taken physics class, you'd call this the acceleration. Acceleration is 2 meters per second squared. And that's physics class, but I'd be okay with this interpretation. Okay, that's it for the video. Now it's time to get into the activity that I've got planned. It's a group activity, and also there's a second part of the video that will take this up. So probably taking up the activity is in the second part of today's video, which you can probably watch tomorrow night to make sure you got what you're supposed to get out of the activity, okay? But that's it for this video. You can probably start the homework once the activity is done.